Hi everyone, I'm Jipeng Liu, coming from Professor Igor Marketing Scoop at the University of Pennsylvania. Crookes radiometer, which was first invented in 1873, can rotate when exposed to incident light. It provided a potential mechanism in light sensing and actuation. However, classical Crookes radiometers can only work at low vacuum pressures, limiting its application to a broader regime for more than one century. Therefore, today we would like to report a first radiometer with microfabricated vanes that can rotate at 1 atmosphere. So in today's demonstration of atmospheric pressure radiometer with metamaterial vanes, we want to first introduce the basic geometry and fluid mechanics of the traditional radiometers. And then we want to describe the fabrication of the 5-flow channel basket weave style nanocardboard and also the assembly of the spindle and LED array. Then we conducted the measurement of the rotation speed and plotted versus the light intensity. Also, we did a comparison between the simulation results and experimental data. Last, we proposed some applications of light sensing and actuation under normal pressures. This slide is a word abstract. You can pause the video if you want to have a closer look at it. So in traditional radiometers, we mainly have a common quad arm radiometer with 4 paper vanes. One side of the paper vane is painted black to absorb the majority of the incident light to make one side of the vane hotter. There are mainly two kinds of forces that uh, makes the radiometer rotates. The first one is the thermal recoil force. The second one is the thermal creep flow. The thermal recoil force, you can understand it as the momentum of the air molecules rebounding from the two sides of the vane. And on the hot side, the air molecules will have a greater velocity and thus greater momentum. The net momentum difference will make a net force pointing from the hot to the cold side on the vane. Another kind of the force is the thermal transpiration flow. It happens at the edge of the vane that the flow will go from the cold to the hot side and also make a net force generated by the thermal transpiration flow to point from the hot to the cold side. So the overall net force on the vane will go from the black side to the right side, the hot side to the cold side. However, both kinds of the forces will maximize at around tens of pascals, which is the main reason that limits the traditional radiometers work at low pressures. Therefore, we're motivated to step out of the low pressure range to explore how to make the radiometer work at normal pressures. We come up with nanocardboard design with microchannels. And there are mainly 3 reasons for our radiometer to work at normal pressures. First, low air density. The air density of the whole nanocardboard is as low as zero point 0.1 microgram per square centimeter. This is 100 times lower than that of the paper. Low, Lower weight means lower friction force. Therefore, our photophoretic force doesn't have to be a lot larger, but everything could be driven under normal pressures. Second, high thermal resistance between the two sides. We use ALD alumina, which is good thermal insulator. And great thermal resistance means we can maintain a temperature difference as large as several kelvins between the two sides of the vane. Third, microchannels. We pattern the microchannels across the nanocardboard because the thermal transpiration flow can only happen at the edge of the vane. Therefore, microchannels can amplify the thermal transpiration flow to make it large enough to drive the radiometer even at normal pressures. Because the thermal transpiration flow is the dominant force when we are dealing everything at around 1 atmosphere. Here's a video of how the radiometer can work under normal insulation. The video is taken at around 1 kilowatts per meter square at noon in one day of the summer. And as you can see from the video, the rotation is counterclockwise, which is the same direction pointing from the hot to the cold side. You can see a little stop and go and not that smooth rotation that as fast as around 4 run per minute in this video. The glass jar is used to minimize the air current disturbances. So the key thing or the key game changer is our nanocardboard, and here comes some microfabrication steps. There are mainly 4 steps in our fabrication. First, the silicon mold creation on the silicon insulated wafer. We used photolithography, reactive ion etching, and hydrofluoric acid release to make this basket weave pattern. This pattern is mainly used to maintain the mechanical stiffness to make it more resistant to thermal deformation. Then we conformally coated 100 nanometer of ALD alumina to increase the thermal resistance. Third, we drop casted carbon nanotube twice to reach a 90% absorptivity of one side of the vein. Then we used oxygen plasma to reopen the nanocardboard channels, which played a critical role in amplifying the thermal transpiration flow. Last, we removed the silicon mold away through blade cleaving and xenon difluoride vapor etching. By making the whole structure hollow, we decreased the air density even more and making the friction force even lower. The whole setup is, as you can see from the photograph on the left side of this slide. We 3D printed a 26 millimeter diameter quad arm hub whose size and geometry matches those of traditional vacuum radiometers. We also built up an octagon array composed of 8 LEDs on the inner side of the chamber. When the vane rotates 360 degrees, it will only experience a 6.5% intensity variation. Therefore, a uniform light distribution is assumed in our chamber, with the maximize reaching 10 kilowatts per meter square. This is 10 times stronger than the natural insulation, as shown in the previous video. We also implemented 8 thermoelectric coolers on the outer wall, which are mainly used to reduce the convection because the LEDs is going to become hotter if you have a great power input. And we don't want a convection to introduce any disturbances to the radiometer rotation. Also, the room air currents are also minimized using glass jar or open-ended transparent tubes, which are not shown in the graph here. The measurement shows that when the light intensity is greater than around 1 kilowatts per meter square, we will have continuous and smooth rotation. But this threshold value is a rough value and is not applicable to all conditions. But the maximum velocity we observed is around 11.6 run per minute at 10 kilowatts per meter square. The rotation speed increases with the increasing light intensity. And the reasoning for this positive relationship could be understood in the flow chart. Like when we have a greater light input, the vein will become hotter because the carbon nanotube on one side of the vein will absorb more energy from the light source. Therefore, the air molecules flowing through the microchannels will also gain a greater energy transferred from the vein, so it will become the air molecules will move faster. Therefore, the thermal transpiration flow or the photophoretic force will become greater with a greater flow-through velocity to make rotation faster. After the measurement, we also compare our experimental data with simulation results. And we find that the simulation results from the finite element analysis and force formulae generally predicts a rotation speed an order of magnitude lower than that of the experimental data. And our guess is that the simulation may underestimate the flow-through velocity and thus the photophoretic force. The rotation of the radiometer can transfer energy to a in air, accelerating it until a new equilibrium is established through the viscous dissipation. Also, by plotting the flow fields of the radiometer, we found that when the rotation is greater than 5 rounds per minute, each vane's flow fields are going to interact with each other, making the undisturbed force formulae not good in prediction. And because we are using the combination of the finite element analysis and force formulae to predict the force, we would like to consider the complexity of the disturbance in the future to make a better prediction. In conclusion, we report the first crude radiometer to work at 1 atmosphere pressure. And the nanocardboard architecture is the game changer because it has low area density, low thermal conductance, and enhanced thermal transpiration flow along its microchannels. Our experimental results reaches a qualitative agreement with theory, which is promising in the future. Also, we propose some potential applications like the microflyers in doldrums, which is also known as wingless waters, or in labs, that they can work at normal pressures without the disturbance of air current. Also, applications like the photogenerators may be also promising in the future if we can increase the rotation frequency by making the radiometer smaller. Last, the next step improvements would be first to make the radiometer smaller so it can rotate at a higher frequency. Also, we may change the pattern a little to try to maximize the thermal transpiration flow. Last but not least, we would like to thank Professor Howard Hu and the staff of the Singh Center for their help with the simulations, fabrication, and characterization. Thank you very much for watching.